Alright, so we have seen how integrals can be used to find out various area problems, but integrals can also be used to find volumes. So volumes using integrals. And first, to find out like how particularly we would do this, let me kind of motivate it through a volume that we kind of know how to find. So let's say if we have a cylinder, right? So a cylinder looks something like this, right? You have the circular base and then you have a height. And we know that the volume of a cylinder, so this is a cylinder, volume of the cylinder is simply V is equal to pi r square h. To motivate why, it's because the idea is if we were to take a cross section of this cylinder, so if I were to like kind of take this cross section, right? What would happen is you'd get a circular sort of cross section. And you can kind of think about the volume as adding up infinitely many of these circular cross sections, and that forms the entire cylinder. And since volume kind of tells us like how much space is enclosed in a shape, the way that like this formula comes about is the fact that at every cross section of of a cylinder, you get a circular area whose area corresponds to pi r square, right? And the amount of cross sections we can take corresponds to the total height, which is h. And since all of these cross sections have this area of pi r square, we're essentially adding up those those areas, and we're adding it up when with like the height h, and so multiplying it with h gives us the total volume, and that sort of motivates how we find out volumes of general shapes. Basically, let's say if you have like some shape and then this is the x-axis and the shape is like a 3D figure and it looks something like this, right? So that's what our shape looks like. And we want to find out what this volume is. If we were to find out a cross section and we added up all the cross sections of this figure, or added up the area of all the cross sections, then once we add up all of those areas, we would end up with the total volume. And that tells us that the volume of any figure, so volume of any figure is simply the sum of all the cross sections. And that's because you have this cross section and you take an infinitesimally small height of that cross section and that gives you a small volume. So let me just redraw it here. So you have that cross section over here and I'm like taking an infinitesimally small dx and that creates a very small shape. And adding up all those infinitesimally small cross sections will give me like an extremely small volume I'm adding up, and adding it up over like the whole x axis that the figure takes on will give me the total volume. And this is very similar to what we did with areas, where we took an infinitesimally small slice of the value that the function takes on. Like if a reminder is like, let's say I had to find the area of this curve, I took an infinitesimally small area by taking dx, which represents that little width, but the height was simply equal to whatever f of x is, and adding it up over all the x's, or like whatever interval I'm interested in, gave me the area. And I'm doing something very similar with when I'm finding volume, except now my slice is an area. So the slice is simply that cross-sectional area, and the dx gives me that tiny height. So this dx gives me a tiny height, which allows my integral that I'm calculating to be a volume. And taking the and taking those like infinitesimally small volume calculations over the entire interval that my figure spans on will give me the total volume. So looking at that kind of tells us that volume is the same, is essentially just the integral from a to b, where a and b represent the upper and lower limits of whatever figure we're worried about, of a of x, and a of x is just the function that determines our cross-section area times dx. And we need that dx to add that little height that gives us that infinitesimally small volume that we want to add up. And so now we have a formula for the volume. And so the idea now, or the challenge, just becomes, given an arbitrary problem, we want to find out the way that our cross section behaves as a function of x. And once we know that value, we can just plug it into our whole integral, and we can use our tools and methods that we know of calculating integrals to then evaluate that integral, and then that will give us the entire volume. And the whole notion of like we can do dx or we can also integrate with respect to dy still stands. But this general like function over here, this general integral, describes to us how we can find the volume of an arbitrary figure. And to put this into better words, our general strategy to find volume is, the first thing we do is we sketch the solid and find a typical cross section. Then we find the formula for cross section. We call that a of x. Find limit of integration, and then integrate. So this is our general strategy, and the bulk of the challenge is on finding the formula and finding the limits. And once you know how to do that, then the problem becomes pretty simple, since we already know how to integrate various different integrals. So let's start off with our first example. We have a square-based pyramid, so problem 1. So we have a square-based pyramid with a square base. Well, let me just draw out the pyramid. So we have a pyramid that kind of looks like this. So this is a pyramid, and like I said, it's a square-based pyramid. So right, and so the size of the square base is, it's 3 by 3 on both sides. This is obviously not to scale, but that's our size of the pyramids. And basically we want to find the volume of this pyramid using using integrals. So if you were to draw an axis over here, we know that the cross section is always a square, and the size or the width of the square continues to decrease as we move towards the left, and the size starts from 3 all the way to 0 at the lower limit, and at the upper limit the size of the cross section, or the size of the width of the cross section, is simply 3. So first we need to find the formula for the cross section, right? So given x, so if x represents the height of the cross section, then the area of the cross section is simply the area of the square, which is x squared. So we found a way to represent the area of a cross section as a function of like x, where x is now like what we determine. So we found out the area of the cross section. Now we just need to determine the limits. So from the lower limit, our cross section has our square cross section has a width or height of 0, and at the upper limit, our square cross section has a height of 3. So we want to find the integral from x is equal to 0 to x is equal to 3. And now we have everything to form our integral. So our integral will just be volume is equal to from 0 to 3 x squared, which is a of x, dx. And evaluating it, we get x cubed over 3 from 0 to 3, and that is just 9, which is our volume. And you can confirm that this volume that we just calculated through the integral is the same as what you'd get when you use your formulas, since we know that the formula, we already know there's a formula to find the area or volume of a square pyramid. So that was a basic example. Let's go to another class of problems that are determined with circular cross sections. So often, a lot of the times, a solid is formed through revolving across like an x-axis, and hopefully what I mean by that is clear through this example. So let's say we have a function f of x is equal to 2 plus x cosine x, and the region between this function and the x-axis on the interval -2 to -2 to 2 is revolved around x-axis to generate a solid. Find its volume. So let me give the graph of 2 plus x cosine x. So between -2 and 2, the graph of 2 plus x cosine x kind of looks like this. And so since this is -2 and this is 2, alright, this is 2 now. So since we're only worried about the region between the x-axis and this function on -2 to 2, this is the region that we're worried about. Let me color it in another color. So this is our region of interest over here. And what the problem is saying is that we're revolving this whole region across the x-axis to form a solid. So if you can kind of visualize us revolving this area across the x-axis, what we're gonna get is when we revolve it, we're going to form a circle as our cross section, and the circle will have like radius equal to whatever f of x is on whatever point we have. So when I revolve this like figure across the x-axis, and let's just take that point as like a point that we're gonna analyze. So this value of x, if I revolve the figure, like what will happen is like the cross section will kind of look like this for that particular point across the x-axis. And so you can kind of visualize how it forms this like circular cross section because I'm revolving it across the whole x-axis. And honestly, to draw this better, because it's symmetrical, it will look like this, right? So alright, so each cross section is this we have the circular cross section that determines the cross section for this particular function when I revolve this function across the x-axis. So what happens is, for this figure, to find the volume of that figure, at each particular point, it contributes this cross-sectional area times dx to the total volume of my figure. And therefore, I found out what my cross-section looks like, and I found out that, or we already were given that my limits of integration were from -2 to 2. And so the integral just becomes whatever this cross-sectional area is times dx evaluated for -2 to 2. And since my cross-sections are circular because I'm revolving the function across the x-axis, what I get is the volume is given by the integral from -2 to 2 of the area of the circle. And the area of a circle at a particular point x is simply, well, the area of a circle is just pi r squared. And the radius at a particular point is simply pi times f of x squared, right? Because our radius, like as we can see here, since we're revolving each point across the x-axis, our radius is simply given by whatever f of x is at that point. And so at each cross-section, our radius will be f of x, and the area of the cross-section will be given by pi times f of x whole squared. So essentially what we're going to be doing is we're going to have our volume be pi times 2 plus x cosine x whole squared. And then because we want to add that volume height, we're going to have a dx over there. And evaluating that will give us the total volume. And you can't do this analytically. So if you were to evaluate this, you'd get about 52.43 units cubed. So that's essentially like the idea of like circular cross sections and revolutions. The main thing is when you're revolving something across an axis, you're gonna get a circular cross section, and then we found out the area of the circular cross section as a function of x, and then we just used our formula for the volume to find the total volume. So let's continue with more examples, because this is a pretty confusing topic and most people will not get it the first time. So in this example, it says that the region in first quadrant between y-axis and graphs of y is equal to cosine x and y is equal to sine x is revolved around the x-axis to form a solid. Find its volume. Alright, so let's first determine what the figure that of interest is. So we're told that we're only worried about the first quadrant, and so we're bounded to the left by the y-axis and bounded below by the x-axis, or one of these graphs. So let's graph sine x. So sine x starts at y is equal to 0, and then it goes like this, and then cosine x just starts at this or y is equal to 1 and then goes down. And I'm just going to specify we only are worried about the first intersection. We don't care about the rest of the intersections. So this is the point, or this region is the region we're worried about. And we know that sine x is equal to cosine x first at pi over 4. And essentially the problem says that we're revolving this region across the x-axis. So we're going to revolve around the x-axis to form a solid. So our cross section essentially becomes kind of like first we're revolving this across the x-axis. So let's just not worry about this bottom part that's not part of the volume. But if we were to think out the cross section, what we'd get is we'd get part of the area that we care about and then part of the area that we don't care about. And to make this clear, let me choose a different color. So this portion in red is what we want to add up in our volume, and then this portion in green is what we want to skip in our volume. But when we do the revolution, right, if we were to take the cross section accounting for both, we'd get circles that consist of both these regions. But we know that like if we were to take this cross section, we can get like two disks. One of those disks consists of the region that we don't care about, that green region, and the other disk, which is the outer disk, consists of both the areas that we have, right? So what I mean is the area the this region, that smaller disk, and then we have this the larger disk over here, consisting of the larger region. And so the area that we care about, that we want to add into our cross section, so a of x is simply this red region, right? So we want to subtract off the circle that is formed by the green region from the circle that is formed by the red region, which represents both the area we don't care about and the area that we do care about. And so let's find the area of the red region. The area of the red region is simply determined by the radius given by cosine x. So that is simply just pi times cosine squared x. And then the area of the green region is determined by the bottom, well, the radius of it is determined by the bottom function, which is sine x. So that is, the area of that will be pi times sine squared x. And so if we subtract off pi times cosine squared x, or we subtract off this bottom region from pi times cosine squared x, we'll only get the cross-sectional area related to the part that will affect the final volume we want to deal with, right? Because if you think about this original figure, what we'll end up with something like this, where we have this like little cone-ish figure, right? And only these parts we want in the volume, and we want to skip out all of these parts in the volume. But because of the way that like we've defined our cross sections, we'll need to do some subtraction. But this is the cross-sectional area that this problem is determined by. And we already know our bounds are from 0 because we're on the first quadrant, and then the first intersection is at pi over 4. So the integral we want to solve is from 0 to pi over 4 of this cross-sectional area, which is simply pi times cosine squared x minus sine squared x dx. And we can solve this by using some trig identities. We know cosine squared x minus sine squared x is another way to write cosine 2x. So this is simply equal to pi times cosine 2x dx from 0 to pi over 4. And then simplifying that, we get that is equal to sine 2x over 2 from 0 to pi over 4. Sine of pi over 2 is equal to 1. So we get pi over 2 minus sine of 0 is 0. So our total air volume is pi over 2 units cubed. So I hope you guys kind of saw this, the reason why we had to do a subtraction. Because what this bottom region, that bottom region was not in our final volume, but it was included in our cross section. So we had to subtract it off in finding the actual A of x. And this method is called the washer method to find volumes. There's more ways, there's more general ways of also finding volumes, but I think I'll cover it in the next part.